Hello, today we are going to learn about permutations. So, I'll use this notation. Box n denotes the first n natural numbers. Okay, and a permutation of n symbols is just a bijective function from n to n. Bijective function sigma from n to n. So, what does bijective function mean? Well, it means that it's a function that is both injective and surjective. So, I'll give you an example. Let's take n equals 3. So, now I am looking at the set 1, 2, 3, and I'll write it down once again, this set. And I am going to write down an example of a permutation for you. So, here I am going to take a permutation. So, it is a function from 1 to 3 to 1 to 3. So, what I am going to do is I am going to show you where each element of this set 1 to 3 goes. So, in my permutation that I am going to construct here, 1 goes to 2. So, this is a function which takes 1 to 2, it takes 2 to 3 and it takes 3 to 1. So, I can write sigma as, so I will call this sigma. So, what we are saying here is that sigma of 1 is 2, sigma of 2 is 3 and sigma of 3 is 1. So, note that this is a bijection in the sense that all the 3 elements 1, 2 and 3 occur here in the right hand side, and of course, since the number of things on the up here and the number of things on this side are the same, each element occurs exactly once. So, basically a permutation is a rearrangement of the numbers 1 to n. So, we will use the notation Sn to denote the set of all permutations on n letters. I will say n letters, so these are n numbers. So, precisely this is sigma functions from box n to box n, such that sigma is a bijection. Okay, so let us see if we can list all the elements of S3. So, I will use what is called one line notation to describe a permutation. So, if I have a permutation sigma, then its one line notation is simply writing down sigma 1, sigma 2, sigma n in sequence. So, if you look at the permutation we had earlier, its one line notation is just sigma 1, sigma 2, sigma 3. So, I will write 2, 3, 1. This is just an efficient way of writing down permutations. So, S3 I am going to try to list all the permutations. So, in one line notation. So, the simplest permutation is where is the identity function. So, 1 goes to 1, 2 goes to 2 and 3 goes to 3. So, in one line notation that becomes 1, 2, 3. So, what you are seeing in this one line notation is that basically you are taking the elements 1 to n and you are somehow rearranging them and writing them again. So, it is a reordering. So, basically what we are going to do is we are going to write down reordering of the numbers 1, 2, 3. So, what else can I do? I can take 1 to 1, I can take 2 to 3 and 3 to 2. Okay, so this exhausts the possibilities where I am taking 1 to 1. If I am taking 1 to 2, then what can I do? I can take 2 to 1 and 3 to 3, or I can take 2 to 3 and then 3 to 1, or I can take 1 to 3, in which case I can take 2 to 1 and 3 to 2 or 3 to 1. So, these are the 6 permutations on n letters. You can ask, okay, so how many permutations are there in Sn? So, what is the size of the set Sn? And this is not very difficult to figure out. So, I have to figure out to write down a permutation, how many choices do I have? And so, firstly, how many choices do I have for sigma 1? So, for sigma 1, well, it can go to any of the numbers 1 to n. So, sigma 1 has n choices. Okay, now having made that choice for sigma 1, how many choices do I have for sigma 2? Well, I have already used up n, so I can't use it again. Sorry, I have already used up the number sigma 1, so I can't use it as a value for sigma 2. So, except for that I can use anything else. So, I have n minus 1 choices for sigma 2. Now, having chosen sigma 1 and sigma 2, what remains are n minus 2 choices for sigma 3. And so it goes all the way. In the end, having chosen sigma 1, sigma 2 dot 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 up to sigma n minus 1, there will be only one element from the set 1 to n which has not been used, and that is going to be sigma n. So, that is 1, and this is just n factorial. So, you see here S3 has cardinality 6, which is just 3 factorial, and if you take a deck of cards, then every rearrangement of this deck of cards is, when I shuffle these cards, every rearrangement is a permutation, right. So, I start with a perfectly sorted deck of cards and then I shuffle it, and then I have a mixed up deck, and the question is how many possible such decks can I get. And so, what is the answer? Well, if you do not have the jokers, then it is 52 factorial, right. It is pretty large. So, that is just what permutations are, but the theory of permutations becomes much more interesting once we take into account certain operations that we can do with permutations. The operation I am talking about is called composition. You see, a permutation is just a function, right. It is a function from the set n to n. So, if I have a function from the set n to n, let us call it sigma 1, and I have another function from n to n, so that is another permutation, I call it sigma 2, then I can compose these functions. This is a new bijection from n to n, because the composition of bijections is still a bijection. And so, what I get is a way of creating a new permutation given two permutations. Let me illustrate this with an example. So, let us take sigma 1 to be our favorite permutation. Takes 1 to 2, 2 to 3 and 3 to 1. So, this is sigma 1, and let me cook up a new permutation which I will call sigma 2. So, this one just takes 1 to 2, 2 to 1 and 3 to 3 itself. And now, how do I compute sigma 2 composed with sigma 1? So, I have to figure out where each of the numbers 1, 2 and 3 goes. So, let us see. So, sigma 2 circle sigma 1 of 1 is sigma 2 of sigma 1 of 1. What is sigma 1 of 1? Well, sigma 1 of 1 is just 2. And what is sigma 2 of 2? Well, sigma 2 of 2 is 1. Similarly, sigma 2 sigma 1 of 2 is, well, so sigma 2 of 2 goes to 3 under sigma 1. So, it is sigma 2 of 3, which is still just 3, and sigma 2 circle sigma 1 of 3. So, 3 goes to 1 and 1 goes to 2. So, you see this is 1, 3, 2. Another way of thinking about this is just under sigma 1, 1 goes to 2, and let us see. So, 1 goes to 2 and then 2 goes to 1. So, I can just follow through this arrow, and that is telling me that under sigma 2 circle sigma 1, 1 goes to 1. And where does 2 go? Again, I will start with 2 and then I will follow through the arrow. So, 2 goes to 3 and 3 goes to 1. So, 2 goes to 3, and then this 3 I will follow through this arrow here. 3 goes to 1 and then 1 goes to 2. So you can compose permutations by simply following through the arrows. Let's try another example. This time we'll take 3 permutations. So let's just add here another permutation. Okay, let's add a third permutation to this mix. So I'm going to add sigma 3, and I'll cook up another permutation here. And this is the permutation which takes 1 to 1, 2 to 3, and 3 to 2. So now I want to know, so I can do this composition. So I want to compute basically sigma 3 circle sigma 2 circle sigma 1. So this, you can think about this in 2 ways. When you think about composition of functions, you can either think of it as composing sigma 1 and sigma 2. So that's what we just computed, and then we compose it with sigma 3. So I'll write down sigma 3 here. And now we need to follow through the arrows between these two. And so if I try to write down the answer over here. So now let's follow through the arrows. So here I go from 1 to 1, 2 to 3 to 2, and 3 to 2 to 3. So surprise, 1 goes to 1, 2 goes to 2, and 3 goes to 3. Okay, or I could have done this in another order. I could have done it sigma 3 circle sigma 2 circle sigma 1. So if I did it this way, then first I would compute sigma 3 circle sigma 2, which means I would follow through the arrows in the 2 lower diagrams here. But let me not do that. The main point to note is that when I did this calculation of sigma 3 circle, then sigma 2 circle sigma 1, then what I was doing was really just following through the arrows through these 3 permutations from top all the way down to the bottom. So if I start here, I can take 1 and I'll follow it down. 1 goes down to 2, 2 goes down to 1, and then that goes down to 1. So 1 goes to 1. 2 goes to 3, 3 goes to 3, and then 3 goes to 2. 2 goes to 2, and then 3 goes to 1, and then 1 goes to 2, and then 2 goes to 3. So 3 goes to 3. So these things are really just the same. There is no difference between whether I compose sigma 3 with the composition of sigma 2 or sigma 1, or whether I compose the composition of sigma 3 and sigma 2 with sigma 1. So this is called associativity. So and during this calculation, we discovered a rather special permutation which basically takes each element to itself. It takes 1 to 1, 2 to 2, 3 to 3. So this permutation, I'll call it the identity. So I'll call it ID. Okay, and this has the special property that when you compose it with anything, it doesn't change that thing. So if I have any permutation and I compose it with this identity, for example, my favorite permutation sigma 1. Now if I compose it with the identity, the second time when I'm following through the arrows, it's as if nothing happened, right? So so sigma 1 identity composed with sigma 1 is sigma 1. And also if I do it in the other way, right, first I do the identity and then I compose it with some permutation. So these are the properties of the identity, that when you compose it either on the left or on the right with any permutation, you get back that permutation. Composition with the identity has no effect on a permutation. The third property that I want to illustrate about permutations is that it is possible to undo anything that you've done. So if I have a permutation taking 1 to 2, 2 to 3 and 3 to 1, then I can find a permutation which undoes whatever I did. So if I have taken 1 to 2, I want to undo it, I want to take 2 back to 1, right. So let's see how to do that. So 2 must go back to 1, and 2 goes to 3, I want to take 3 back to 2, and 3 goes to 1, I want to take 1 back to 3. So this is what we call the inverse function, right, in set theory. So if this were sigma, then this would be sigma inverse. And what can we say about the composition of sigma with sigma inverse? Well, sigma inverse circle sigma is, well, you follow through the arrows, it is the identity. And in the same way, sigma circle sigma inverse is also the identity. So to summarize, what we've seen about permutations is that this set Sn of permutations of n comes with a binary operation. A binary operation is just an operation which takes 2 inputs and gives you 1 output. So here the 2 inputs are sigma 2 and sigma 1, 2 functions, and it goes to sigma 2 composed with sigma 1. And this binary operation satisfies the following axioms. The first axiom I will write as associativity, which says that for any 3 permutations, sigma 1, sigma 2 and sigma 3, we have this sigma 3 circle sigma 2 circle sigma 1 is sigma 3 circle sigma 2 circle sigma 1. Then we have the existence of an identity. So there exists identity, and I mean, we know in this case what it is, and so there exists which satisfy the property that sigma circle identity equals identity circle sigma for all sigma in Sn. Well, I should have said here for all sigma 1, sigma 2, sigma 3 in Sn. And the last property is the inverse property. That is, for every sigma in Sn, there exists an element sigma inverse in Sn, such that sigma circle sigma inverse equals sigma inverse circle sigma, and both of them are equal to the identity. So these properties of permutations taken together abstractly give the definition of an abstract group, which we'll talk about next time. Thank you.